So chapter 6 kicks off with a deep dive into antiderivatives. So we've done things with the integral. The integral we've looked at from a geometric standpoint. We looked at the integral from a Math 9 standpoint. A little bit of the basic easy antiderivatives, but this is where we're like going to get into all the different antiderivatives. So there will be some new things this chapter we skipped last year. Okay, we did use substitution, we did separate and integrate, but there are going to be a few other things. There's something called Euler's method that we didn't do last year. There's integrating partial fractions, which we didn't do. So we're going to start seeing some of the new things that we skipped. Okay, but today it is stuff you've seen before. We're going to do the antiderivative. We're going to do general and particular. That means plus c, or with an initial condition to solve for plus c. And then we'll do separate and integrate will be tomorrow. Most of this is just laying the groundwork. So on slide number 3, remembering that, don't forget every antiderivative has the plus c on that, which is called the constant of integration. You always need to include the plus c for every antiderivative. If you're given an initial condition, that means of x, y value, you'll be able to find the specific plus c that goes with. So that'll make it a specific solution instead of a general solution. So if you were like, this is a basic one, right? You should be able to do the antiderivative of this. So we would say the antiderivative of 2x is x to the second. And the antiderivative of cosine x is sine x, and then plus c. So that is called a general solution because it's left with a plus c that's not a number. We don't have enough information to do the number. So the rule of thumb is that any power, you add and divide by the new power. So if you start with n as your power, you add 1, and then you also divide by the new power. That will be true for every situation except -1 as a power. Because if you try and you add 1 to -1, what power would you result in? And then you would have to divide by 0, which is a problem. And so having n to be -1 has its own special antiderivative. And the antiderivative of 1 over u du is the natural log with the absolute value. Don't forget that. So that is, I find some people doing natural log when they're not supposed to. They do natural log to -2 powers. -2 powers are not natural log antiderivatives. It's only powers of -1. So if you can rewrite it with a -1 power and make it 1 over u du, then you have the natural log with the absolute value. Otherwise, you add 1 to the power and divide by the new power. All the trig antiderivatives, those you should be fluent in that. You should be comfortable moving back and forth between the various derivatives and antiderivatives. This time, the cos don't have, like cosine doesn't have a negative in its antiderivative. It's positive sign. It's the sign that has negative for its cosine, but you should be familiar with all those. You should be familiar with these antiderivatives of exponentials. So e to the u du, remember that its derivative is e to the u times the natural log of e times the chain rule. Here it's going to be e to the u divided by, so it'll be e to the u divided by the natural log of e and divided by u prime, or du dx, and then plus c. So make sure that you are remembering it's the anti-chain rule now. We're dividing by that value. A to the u divided by the natural log of a, and then the chain rule of du dx. So it's the division. the antiderivative of the natural log of u. Okay, we don't have that yet. We're going to have to wait on that one. And we'll develop that in a different lesson. Okay, here are the 1/overs. Most of the time, these 1/overs have a antiderivative that's linked to them. We've already seen 1/u du, because that is u to the -1 du, and that's the one that would result in the natural log of u, absolute value, plus c. The other ones that are 1/overs, if they match the format, they're going to be an inverse trig. So what's that first one with the square root of 1 minus u squared? Do you remember what that antiderivative is? Or the inverse of sine or cosine. So it's either sine inverse of u plus c or cosine inverse of u plus c, depending on if it's a positive or a negative. So you should recognize, since that square root represents the derivative of the inverse cosine and sine, then the antiderivative would be connected to that. What about the next one? Inverse, right? Okay, so it's either tan inverse of u plus c or cotangent inverse of u plus c, depending on, again, if it's plus or minus. Which means the last one is your secant inverse or cosecant inverse. A lot of people recognize that one because of the absolute value. The absolute value helps be a kind of a dead giveaway, and then the square root of u squared minus 1. So the AB class is just learning these as derivatives for the first time, so they had a quiz on that yesterday. So you should recognize it going the opposite direction. So any questions about the basic antiderivatives? Refresher. All right, so your strategy is to recognize common forms of antiderivatives. And then the second part would be to solve for C if given an initial condition f of a equals b. So you'd be given an x and a y value, a being the x value, b being the y value. If you're given that, you can solve for C. So find all the functions that satisfy this antiderivative. So what you're going to want to do first is you're going to want to move the dx over to the other side, like this. Okay, so that's that differential, that dx part. Because it's an x value, move it over. And then you're going to integrate both sides. So the antiderivative of dy is regular y, and then the antiderivative of each piece, so 3x squared would be 3x cubed divided by 3, and then plus sine, and then plus c. In other words, just x cubed plus sine x plus c. So that's a general antiderivative. And plus c represents the vertical shift that moves it up and down. All right, now, the next ones we're going to be given an initial condition. So the initial condition enables you to find the unique value of c, which would be a particular solution, okay? You go from general to particular, non-specific to specific. All right, so here's another one. Find the particular solution through e to the 2x minus 3x, going through the point 1 comma 1/2. So you'll want to separate the dx, the differential, to the other side, and then integrate both sides. So y is going to be equal to, so the antiderivative e to the 2x is e to the 2x and then divided by two things. It's divided by Linney. It's also divided by 2. And then minus 3x, that'll be 3x raised to the second divided by 2 plus c. And then at that point, you can move to find the specific solution by plugging in 1 for x and 1/2 for y. So that'll be 1/2 equals e to the 2 over 2 minus 3 over 2 plus c. Okay, how do you want to solve that? What would you guys do first?
Could you add the 3 over 2 to the side?
What would you get?
2.
Yep. 2 equals e squared over 2 plus c, which means c would be 2 minus e squared over 2. So that's your c value, so then you should have a specific solution. So y equals, I'll write it as 1/2 e to the 2x, that's the same thing as e to the 2x over 2, minus 3/2 x squared, plus the constant 2 minus 1/2 e squared. So that's our, what's called a particular solution or a specific solution. All right, here's another one. Find the solution to the differential equation f of x equals cos x squared, for which f of 3 equals 5. All right. So f of x is going to be the antiderivative. So maybe you want to, I don't know, write it in dy dx if you like. I don't know, say this is dy dx equals cos x squared, and then move the cos x squared to the other side. So you have it like this, and then antiderivative. I mean, if you like, it depends if you like the primes or the other, but we could say then f of x is going to be equal to, okay, do you guys know the antiderivative of the cosine of x squared? It's not. It doesn't work that way with, no. Doesn't, yeah, the x squared. It doesn't work that way with variables. It only works that way with, like, if it was a 2x, that would work. Like the cosine of 2x. You could do sine of 2x divided by 2, because the chain rule would just be a number, but you can't do it with variables. Okay. All right, so that means we can't do this. Okay, we're stuck at the cosine of x squared dx. But we do have an initial condition. So this goes back to last chapter. We can say that my plus c is going to be plus 5 if I start with a lower bound of 3. And then my upper bound is unknown. Okay, we don't have an upper bound yet, so that would be your variable. That's as far as that is the solution. Your calculator can graph that, your calculator can do stuff with it, but that's as far as you can take that. It's an expression that you write, and it's not necessarily an antiderivative that you find. So you have to be okay with saying, okay, the solution is going to be expressed differently. And remember, it's going to express, it's the area from 3 to whatever, knowing that when you're at 3, you've already covered an area of 5. You have that already. So the 5 is the initial condition, the 3 is your lower bound, and then our upper bound is unknown. We can use that then to find any other f value. I could find f of 5. I could find f of 10. I could find f of 0 once I have an expression for f. So be comfortable leaving it in a what looks like an unfinished integral.